In this video, we're going to talk about the enthalpy of solutions. Previously, we mentioned that as you break, say, the bonds between ions and get water to solvate it, you're breaking some bonds and making new ones. And depending on the relative strength of the ion-ion interactions versus the ion dipole-water interactions, this may be exothermic or endothermic. Let's explore a little bit of what's going on there. There's basically situation where, say, we have salt. We'll go with sodium chloride solid. We're going to add it to water, and we're going to get sodium chloride aqueous. What's really happening here, again, is we've got pluses and minuses, and I've got some waters. And the waters had been interacting with each other, having reasonably good interactions in the past. And what we have to do is start breaking a bunch of bonds. Two things have to happen. I've got to break ion bonds, but I also have to break water bonds to other waters. Separate these intermolecular forces to pull them apart. Well, there's going to be some overall change in enthalpy for this reaction. And this reaction is just the solvation. So we really think of this as the delta H of the solution of the whole thing dissolving. What that's going to involve, though, is all the individual steps. So this is going to involve some energy to break the ions. This is going to be whatever our solute, the thing we are dissolving. And there's also going to be some energy to break those waters apart. So there's some enthalpy of the solvent, the liquid doing the dissolving. Both these are going to require energy to be put in. So we're going to have to add energy to the solute to break those ions apart. We're going to have to add energy to the water to break those waters apart. That's true even not for ions. Any solid material, you're going to have to pull apart from the rest of the material in its lattice. But then they're going to start pairing up. You're going to get negative ions will have attractive forces to the hydrogen side of some waters. Positive ions are going to have some attractive forces to the negative side of some waters. And this will eventually stack up as more and more waters get involved. Well, these are forming bonds. These are giving away energy. And so there's also a delta H here for that mixing. As the solvent is then able to surround and interact with the solute, it's going to give away some energy. So we have some positive delta H's for breaking our materials apart. We have a negative delta H for them interacting with each other. All this is going to be our delta H for that overall reaction, solvating the sodium chlorides, the delta H for the solution, for making that solution from the solid and the water. This is true for any solvent and any solid, really. In water, we tend to have these values calculated out, and so the terms can be a little bit different. Delta H of the solution, in terms of when we want to talk about ionics in water. Well, what is holding the ions together? It's the lattice energy. So really it's the delta H of the lattice energy plus the delta H of hydration. In this case, hydration takes into account water breaking apart and then water interacting with what amounts to gas phase ions that we would get in the lattice energy. Since most of chemists' work is done in aqueous systems, tables involving water tend to talk about the hydration so that I don't have to solve water breaking apart every time and the individual mix energy every time. Instead, this has been standardized for dissolving these ionic materials in water. So we can look up the delta H of hydration for various materials, as well as the lattice energy for that same material, in order to find what is the delta H of solution when I want to dissolve an ionic compound in water. Well, depending on the difference here, depending on how strongly water interacts with those ions versus how much energy it takes to pull apart the ions, delta H of solution could be positive or negative. If I have a positive delta H of solution, then I have to add energy. That effect is it takes more energy to cause it than it gives off when the waters interact with the ions. In this case, this is endothermic. This will actually cool a solution. This is how we make cold packs. Things like ammonium nitrate. When they dissolve, they actually require enthalpy. They will cool down the solution as they dissolve. If you have a negative delta H, then the amount of energy released through the mixing is much greater than the lattice energy required to break things apart, and so as a result, this tends to be exothermic. Things like calcium chloride are quite exothermic. Other things like acids, getting H plus to spread around water is quite exothermic, to the point that in general, it's very dangerous to mix water with acid. You have to do it in specific ways and very carefully and slowly, because it is so exothermic, it can locally cause the water to turn to gas and then splatter very concentrated acid everywhere. And so depending on the balance of our lattice energy versus our hydration, we can get endothermic and exothermic reactions. We can make cold packs and we can make hot packs. So why does that happen? It kind of makes sense for exothermic. It's releasing a lot of energy, which then provides more energy to break more of the solids apart. And so that ought to be fine. But if you're endothermic, you're cooling down the material. It becomes harder and harder to break the solid apart. Why does that work at all then? Well, if we think about a container, and I have a little bit here of ammonium nitrate. Remember that favorite graph in all chemistry, there's a distribution. While most of our molecules are nowhere near energetic enough to cause our molecules to break apart, a few of them are. There's always a couple. And so little by little, a few of these will break free. Not a lot. And honestly, if they drift back in, they'll just stick right back to the surface. But they have a large volume to spread out in. By random motion, yes, sure, some come back, but others drift really far away. And that effect is, again, this is kind of an equilibrium argument. There's a leave rate, and even if it's not that great, because there's always some particles past that energy, there is the ability for some of these to break free into solution, even though they'll consume some of that enthalpy when doing so and cool the whole solution. Well, as more and more show up, we start to get a return rate. Eventually, our return rate will indeed match our leave rate. There's only so much you can get dissolved. But that propensity to spread out and move further away means that there's plenty of time for another one to break free and start going, and another to break free and start going, which means that for a while, the solution is going to keep getting colder. Anytime one of those particles returns, it would give off that energy. It would be exothermic to form the solid again. But for a while, there's a favorability for the leaving, which is the endothermic. This is why the solution gets colder. Until you've reached a solubility where the return rate is the same, it's still going to favor breaking apart. This is an argument that stems from entropy, which you discuss much more in 163. But it's a component of what actually makes reactions happen. It's not just the enthalpy. There's also a component of how likely is a reaction to go one way or the other. Early on, this reaction is much more likely to go in the direction of the solid breaking free than it coming back, even if that's the endothermic. But because there's always a few particles that have that energy, it's going to happen. And so you will cool this solution down for a while. This is how cold packs work. Here we have the introduction to the idea of what's involved in the energetics of getting something to dissolve. We have to break apart the solid, we have to break apart the liquid, and then we have to account for the energy released when they then start interacting with each other. Whatever the balance of all those is will determine what the change in enthalpy for the overall system is, whether you'll heat up or cool down your solution, based on whether it's exothermic or endothermic.